Hello everyone and welcome. So today we're going to be talking about the method of partial fraction decomposition. For some of us, this may be old news. This is something that you might have seen back in Calculus 2. At that time, it was a method used to simplify rational functions so that we can find their antiderivatives. Now we're going to be using that same technique of breaking up rational functions into simpler parts so that we can find their inverse Laplace transform. So what is it that I'm talking about here? Well, the idea is this. We have a rational function here, which is a polynomial over polynomial. And it turns out that there's a way to figure out that, well, first of all, we can factor the denominator there. And then it turns out that there's a way to break that up into simpler rational functions that we can then work with a little bit more nicely as individual things. So certainly these two things that we have over here on the right-hand side are much easier to work with than the thing on the left, which is much more complicated. You probably at this point can find the reverse or the inverse Laplace transform of each of these individual functions on the right. But just looking at that first one and knowing what to do with it, we don't have anything for that. So this new form is easier to work with, but how do we get to it? How do we get to knowing what the denominator should be and what the numbers are that should go on the top? That's what we need to figure out. And that's what the method of partial fraction decomposition is for. So let's get into it. There are three major steps in this process that we need to know how to carry out. The first one is to factor. So remember, a rational function is one that has the form polynomial divided by polynomial. So we're going to call the polynomial on the top p of s and the one on the bottom q of s. So for this technique to work, first of all, the degree of the top has to be lower than the degree of the bottom. If that's not the case, you can always make it happen by doing a polynomial long division. Then you'll be left with, you'll have a polynomial at the beginning, and then this rational function here will be the remainder, and we can work with that. So in any case, once we have it into that form, the first step is to factor the denominator as far as possible, factor q of s. And you may or may not realize that when you are factoring something over the reals, there are only a certain number of things that can come out at the end. If you've done it all the way down, then you really only have two kinds of things. We're going to break it up into four different kinds of things that can happen. So the first thing that can happen is the standard thing, the thing that you kind of most want to happen, which is that you can have a simple linear factor. So s minus alpha, s minus something. We're using s as our variable here because we're going to be doing this mostly on the Laplace side of things. So you can have a simple one of those, just one copy, or it's possible you could have a repeated linear factor, right? So you could have s minus alpha raised to some power. If that's 1, then that's the simple linear factor, but you might have a square or a cube or things like that. The other thing that can happen is that sometimes you can get what's called an irreducible quadratic. Right? An irreducible quadratic is something that has a square term, right? It's a polynomial with a square term, but that can't be factored further. How would you know that it can't be factored further? Well, the easiest way to tell is using the quadratic formula. The quadratic formula says that it will tell you your roots, and if you have an irreducible quadratic, what you'll find is that the roots are imaginary or complex, right? They have a complex part or an imaginary part. And if we write it in this form, which is the standard form we see in the textbook of s plus 2 alpha s plus beta squared, then the way you can tell it's irreducible is if that beta squared is bigger than the alpha squared. So you're comparing the coefficient of s divided by 2 and then squaring that, and that has to be smaller than the constant coefficient, right? And that's basically the discriminant if you tried to solve this by the quadratic formula. So irreducible quadratic factors, these have complex roots. If the roots are real, then you can factor more. If not, you're stuck like this. So we can have irreducible quadratic factors, and we can also have repeated irreducible quadratic factors, so we could have them raised to some power n. The form of these factors that shows up determines what the decomposition will look like on the other side, right? It'll tell us what pieces we have to put together in order to do a partial fraction decomposition. So let's look at, for each of these four things that could come up, what do we have to put on the other side? All right, so the first two are the linear factors. If you have a simple linear factor, then on the right-hand side, you're going to get just a constant over that factor. Simple. No problems. If, however, the linear factor is repeated, then you have to have a cascade of these things. You have to have the same linear factor, just over here on the right-hand side, but also you have to have a constant over the square of that factor, the cube of that factor, all the way up to whatever the power is of the original thing. All right, so the nice thing here is that you always get a constant on top, so that's going to make things simpler, but you do have to have all of these different terms. So if you had a cubed term, you would need a cubed factor in your factorization. Then you have to put 3 terms on the right-hand side. All right. So when n equals 1, these are the same. These things, front and top and bottom, these are the same. So you can just memorize the more complicated looking one. That would work. So they're the same thing. And then we're eventually going to have to figure out what the coefficients A1, A2, A3, and so on are. We're going to do that later, and it's going to work a lot like the method of undetermined coefficients. Okay, so that's the first 2 kinds of things, the linear factors and the repeated linear factors. What about if you have an irreducible quadratic? If you have a simple irreducible quadratic, s squared minus 2 alpha s plus beta squared, then you get something that looks like, well, the top will be, instead of just a constant, will be bs plus c. So you do something that is linear on the top. You need both the s and the constant there in order to make this work. And then the bottom will be the same polynomial, the thing that you factored, s squared minus 2 alpha s plus beta squared. If you have a repeated irreducible quadratic factor, it works just like with the repeated linear term. You have to have one of these terms with the powers going up for each of the powers of the irreducible quadratic that you have on the left-hand side. Right? So it seems like a lot to remember, but just remember this. You get one term on the right-hand side for every power of the factor. And then you always put on the top something 1 degree lower. So if you have a quadratic on the top, on the bottom, you put a linear term on top. If you have a linear term on the bottom, you put a constant on top. That's it. You can put it together. So let's see some examples of how exactly this would work. Well, sorry. Oh, got ahead of myself there. We're not going to do that yet. First, we're going to talk about the third step, which is that you have to figure out the coefficient values, right? Every one of these steps that we've looked at before has introduced these unknown coefficients, b, c, and a, right? And we're going to need to know what those are in order to have something that we can really work with. So how do we do that? Well, the first step is going to be to get all of the terms on the right-hand side, all of the things that we put over there and separated. We're going to pull them back together on top of a common denominator. The common denominator will always be the same as the original denominator. Right? So then, once the denominators are the same, since the functions have to be equal on the left and right-hand side of this equation, the numerators have to be equal. So we can just get rid of the denominator at that point. And then we need to figure out the coefficients to make the 2 sides equal. And there's a couple of ways we can do that, as we saw back when we did undetermined coefficients. One way is you can just look at the common terms and make their coefficients equal to each other. So you look at the constant terms and the s's and the s squareds and the s cubes, and you set their coefficients equal to each other, get yourself a series of linear equations. The other option is plugging, left out a g there, plugging in convenient s values. Right? So plugging in convenient s values. So you can, what we're trying to do is make 2 functions equal to each other. That means they have to be equal at all possible variable values. So you can just pick whichever ones you want if it's convenient. All right, so now let's actually try to do this a little bit. So here I've listed 5 different functions, and I would like you to try to tell me what the right-hand side of the method of partial fractions should be. So on the right-hand side of this one, so for example, let me just go through the first example, then I'll ask you to do some of these yourself. All right, so for the first one, well, the first step is to factor the bottom. Oh, gotta get my pen. So we need to factor the bottom. This is 5s minus 4. The top is going to be unchanged. The bottom, we can factor that as s plus 2 and s plus 1. And once we see that, we have 2 simple linear factors. So it will have to be a over s plus 2, and then some other constant, can't be the same, over s plus 1. Call these constants whatever you want. All right, that's all I'm asking you to do for this. Let's just find the right form. And we'll do an example following this of actually going in and figuring out what the constants are. All right, so now I've changed it by having the bottom be s plus 1 squared times s minus 4. So I'd like you to pause for a second and figure out what you think the right-hand side should be, and start up again. Okay, so hopefully what you got was, since we have s plus 1 as a repeated linear factor, we're going to have a over s plus 1 squared and b over s plus 1. And then that's it for that linear factor. And then you have the other linear factor, which appears once. So we get a c over s minus 4. All right, so hopefully that's clear. All right, now let's try it again. Here we have a triple linear factor, and we have what looks like a quadratic, irreducible quadratic. Now, you should always check to make sure that your irreducible quadratic really is irreducible by seeing if it has real or complex roots. All right, so give that a try, and take pause and see what you got. Okay, what I think you should get is, first of all, for the quadratic, it is in fact irreducible, and you should get as plus b over s squared plus 2s plus 8. And then we have a power 3 linear factor here, so we're going to need 3 more terms, c over s minus 2 cubed, plus d over s minus 2 squared, plus e over s minus 2. And it is, you do in fact need every single one of these terms. Now, sometimes those coefficients might end up being 0, but usually they're not. So you have to have everything available in order to be assured that this method will actually work. All right, a little bit more involved this time. So notice, so far, it does not matter what what the numerator is. For determining the form, all that matters is the denominator. Right? So keep that in mind. All right, a little bit more complicated one here. Here we have 4s to the 6th minus 5s to the 4th plus 3s minus 1 over s squared plus 4 to the 3rd times s squared plus 1. So these are irreducible quadratics, even though they don't have the middle terms. And the question is, what should the right-hand side be here? So again, I'll ask you to pause and write down what you think the result should be, and then come back in a second. Okay, so let's see. We have this irreducible quadratic 3 times, so we're going to have to go with 3 different terms. Whoops, let's try and do it right though. Here I might run out of letters, so I'm going to start doing subscripts. So we might call this A1s plus B1 over s squared plus 4 cubed plus A2s plus B2 over s squared plus 4 squared plus A3s plus B3 over s squared plus 4. That takes care of the term s squared plus 4 3 times. And then lastly, we have the 1 over s squared plus 1. We have A4s plus B4 over s squared plus 1. All right. Hopefully that's what you got as well. All right, and then finally the last one, we have 1 over s squared plus 4s plus 3 cubed. So give that a try and give it a pause, and then come back when you've got yourself an answer. All right, well, if you treated this as a irreducible quadratic, then the trick question has tricked you. This is factorable still. This is not fully reduced. It turns out that s squared plus 4s plus 3 can be factored as s plus 3 times s plus 1. And then that whole thing is cubed. So what we really have here is s plus 3 cubed and s plus 1 cubed. We have 2 degree 3 linear factors, not a degree 3 irreducible quadratic. So what does the form of this have to look like? Well, we're going to have a1 over s plus 3 cubed plus a2 over s plus 3 squared plus a3 over s plus 3 plus a4 over s plus 1 cubed plus a5 over s plus 1 squared plus a6 over s plus 1. All right, so let's hope we don't run into anything quite that long in the future, but this is how you would break that down. So you do have to be careful that you really have an irreducible quadratic rather than something that can be further factored. And you do that by checking the roots. All right, so just be careful to make sure you're really following the method all the way through. Don't always trust the things that show up on the paper to be what you initially think they are. All right, so last but not least, let's try to do this all the way out. We've been figuring out the proper form, but let's actually figure out the coefficients that go with it. So here's an example for us. We want to find the partial fraction decomposition of 2s squared plus 7 over, 3s squared plus 7 over s cubed minus s squared plus 9s minus 9. All right, so where do we begin? We begin by factoring, yes. So we have to factor the bottom here, s cubed minus s squared plus 9s minus 9. We can do this by grouping. We could pull out an s squared from the first two terms and have s minus 1. And we can pull out a 9, and that leaves us with an s minus 1. And so we can see that this is s squared plus 9 times s minus 1. And this can't be factored any further. S squared plus 9, s squared plus anything positive is an irreducible quadratic. So now we have the form of the denominator. We have 3s squared plus 7 over s squared plus 9 times s minus 1. And so what does the right-hand side of this look like? Well, it's going to look like as plus b over s squared plus 9 plus c over s minus 1. Now it's on to the step that we haven't actually carried through yet, but that I described earlier, which is we have to get ourselves a common denominator here. So that means this first term has to be multiplied by s minus 1. So we get as plus b times s minus 1. And the second term, the c, has to be multiplied by s squared plus 9. And then the whole thing will be over s squared plus 9 times s minus 1. At this stage, we can drop the denominators and just equate the numerators. So we get now 3s squared minus 7 is equal to, and let's see what we've got here. So we have as squared plus bs minus as minus b plus cs squared plus 9c. So let's gather our terms together. The s squareds, we have a plus c times s squared. The s terms, we have b minus a times s. And then we have minus b plus 9c. Not sure why I'm doing a lowercase c there. Okay, so now we can just take the two sides of this equation and set the coefficients equal to each other. So the s coefficients on the two sides of this equation are 3 and a plus c. The that's the s squared coefficients. The s coefficients are 0 and b minus a. And the constant coefficients are minus 7 plus and will be equal to minus b plus 9c. All right, so what can we see here? Well, from this equation, we have that a equals b. So we can convert this whole thing into two equations. We get b plus c is equal to 3, and minus b plus 9c is equal to minus 7. Oh, why did I say minus? These are pluses. So, always fun to have a sign error. So let's see if we can correct them all. Got a plus there. Sorry about the confusion. All right, so we're back on track. Now, if we add these two equations together, we get 10c is equal to 10. So c equals 1. From c equals 1 and b plus c equals 3, we know that b is equal to 2, and we know that a is equal to b. So a is also equal to 2. So what we get in the end, if I can add another page here, is that s squared plus 7 over s cubed minus s squared plus 9s minus 9 is equal to 2s plus 2 over s squared plus 9 plus 1 over s minus 1. Let me just take a quick check. Yep, there we go. So if we wanted to find the inverse Laplace transform of this, it would be the same to find the inverse Laplace transform of that. So this is a way of simplifying things. At this point, I would say challenge yourself, try to actually find the inverse Laplace transform of the function that's